Welcome back to Trees of Life. I'm Dr. David Ronderos. Today I'm speaking with Dr. Martin Nowak. He is a professor of mathematical biology and teaches and does research in the area of evolution at Harvard University. I'm here with Dr. Martin Nowak, and do you say Nowak?
Nowak,
Okay, so Dr. Nowak is evolutionary biologist, mathematical evolutionary biologist at Harvard.
Mm-hmm.
And I have to say that when I read your biography description online, I thought this is like the most interesting bio I could ever read. It is like all of these fascinating topics about evolution and mathematical biology and the origins of language and all kinds of fascinating topics. So why don't you just start by telling us a little bit about what you do? What's your area of research?
Mm-hmm. So it's great to be here with you. And what fascinates me is really the fact that biology and especially evolution has become very mathematical over the last few decades, and that mathematics is very useful and in some sense even necessary to understand evolution and therefore all of biology. Because the saying is nothing in biology makes sense if not seen in the light of evolution. But evolution is a process that really has to be studied with mathematical equations, and that's what we are doing.
Yeah, that's interesting because when you think about the history of science and the mathematization of natural phenomena, it seems to many people at first glance at least that biology is kind of a very messy sort of contingent process, and one can ask, well, does math really have anything to do with biology? What are some examples of ways that math can teach us things about biology and evolution that we couldn't know otherwise?
Yeah, so it's a good question. So that attitude is more or less the attitude that I got when I started to work in this field more than 30 years ago, that you always had to explain how can it be that there is something like a mathematical biologist. But if you look back in the history of science and also philosophy, Plato already and Aristotle held mathematical knowledge in a very high regard. But they put it higher than sort of common knowledge about the world, but not as high as the intuition of the forms themselves. Later then started the time when mathematics was realized to be very important in physics, and I would associate this very much with Kepler, also Galilei to some extent, but Kepler was the first scientist who believed in a physical reality of a calculation. So if a calculation gives you a certain result, that's not just a magical trick, that means something in the world of physics. And that really was 3 centuries before mathematics became really important in biology. So we are slower than physics. But at the time of Kepler and Tycho Brahe, and so it was also clear that the heavens were perfect. The heavens sort of would require mathematical explanation. But the Earth here was so messy that, as you said, a mathematical explanation is not possible and not even thinkable. But that is, it's no longer like that. And even Darwin formulated evolutionary theory as a verbal theory, but he himself said he wished he had a mathematical sense because that gives you an additional intuition, which he doesn't seem to have. And then when you think of Gregor Mendel, who discovered, of course, genetics and inheritance, the curious fact about him as a student at the University of Vienna, he was a very good mathematician, but he failed botany. And he failed botany twice, and then he gave up the idea to become a scientist. He became an abbot. But he did his experiments with peas. But even then he's described as somebody who has a very strong mathematical intuition. He was looking for a kind of result that he believed would be the case on mathematical reasons, which he then kind of confirmed to some extent with his experiments. So I think a good example of what mathematics does in evolution is, if you ask what is natural selection, ultimately, natural selection is an equation. So it is a description how different types reproduce in a population at different rates. And without that description, you don't really understand what natural selection is.
Very good. And so then so Darwin, and you in your talk earlier today, you laid out beautifully some of the history of the other thinkers that led up to Darwin. So you have Darwin with his idea of natural selection, and then Mendel, and the two insights from these great geniuses of biology don't get really synthesized until much later, right? This is with people like Sewell Wright
Yes, that's right.
and R.A. Fisher.
So Darwin didn't know how inheritance worked, and he believed in blending inheritance. So blending inheritance would be there's a continuous rate, and say if the father is 1 meter 80 and the mother is 1 meter 70. I use European. Yes, so then the child would be sort of 175. That's the average. So that's called blending inheritance. And that creates a problem because then everybody interbreeds. After some time, everybody has the average height and there's no evolution going on anymore. This was a problem that was pointed out to Darwin by a British engineer. And Darwin didn't know how to resolve that problem because he didn't know Mendelian inheritance. He didn't know that Mendelian inheritance is not continuous but particulate. So it's like a digital system that gets sort of reshuffled, and therefore it is not just a numerical average of something. And Gregor Mendel's work was published in 1865. Darwin could have read it, but he didn't read it. It was kind of hidden away in the Brunn Academy of Sciences.
Yeah. So one of the questions that comes up with evolution, and we mentioned natural selection already, that you have some people who see nature as red in tooth and claw, as they say, and people look at evolution and say, oh, there's a lot of death out there. But
is that the way we should think about this?
Yes, but
is there another option?
Yeah, very good question. So it was in the classical formulation of Darwinian evolution and also neo-Darwinian synthesis, and you mentioned Sewell Wright and there's Ronald Fisher and Peter Snowden. The two fundamental forces of evolution are mutation and selection. So mutation generates variation, selection then determines who wins and who loses. So this is kind of Darwinist in the sense that it's very fleeting because it's always about winning and losing. It's all about competition. So over the last 20 years, I have actually worked on that problem of cooperation.
It's lovely, isn't it?
Yeah.
That's okay. Yeah.
So in the classical formulation of evolution, we have this instrument for simulation and selection, and it is really based on all-out competition. But I have been studying cooperation for the last 30 years, and sort of accumulate increasing evidence that cooperation should really be seen as the search fundamental principle of evolution. So it's not just mutation and natural selection, it's also cooperation. And cooperation means that individual cells, animals, humans help one another, and is helping to make common goals, and the other person is a benefit. And cooperation is really necessary to explain the complexity that we see in the biological world. So I have argued that cooperation is necessary for the origin of life itself. For the first cell, the normal cells, the evolution of the genome, which can be seen as a cooperation of different genes, for the evolution of multicellular organisms, and then also that which is giving rise to humans.
That's fascinating. So cooperation then, this is where you have one unit, I'll say, because it doesn't even have to be an animal, right? And it's not just animal that behaviorally cooperate with each other.
Cells.
And cooperation then gives rise to these sort of emerging abilities that you see. There's multicellularity or population level cooperation or different forms of symbiotic relationships or kin relationships. What are some of the ways that cooperation can work?
So as you have said, cooperation leads to these new levels of biological organization. And it depends to think what is in nature. So wherever we look, we find examples of cooperation. The cells are body component. And breakdown of the cells, breakdown of cooperation in the cells of our body is cancer. Cancer is an evolutionary disease. So we see cooperative phenomena being important every day. And then the question is, how do they arise? If natural selection a priori opposes cooperation, so if natural selection is competition, would sort of favor defection over cooperation, because cooperation entails a cost and will benefit somebody else, and the other person or the other cell is a competitor. So how does natural selection have any ability to actually favor cooperation over defection, and where the mechanisms come? And there are many thousands of papers that have been written on this topic. And in 2006, I have summarized them into 5 mechanisms. And these are interaction structures. And these interaction structures then explain how natural selection can favor cooperation over defection. And examples here are direct reciprocity and indirect reciprocity. And then we have, so there are 5 mechanisms. And then we also have spatial selection, individual selection, and keep.
Fascinating. And for those that want to learn more about these particular mechanisms, several of Dr. Nowak's books go into great detail on this. So you have written Super Cooperators, and I also have your book, Evolutionary Dynamic. Now, another interesting topic I want to visit with you about relating to evolution is the harmony of faith and science. So you're a Catholic, and we're here at the Society of Catholic Scientists meeting today. And how do you view the relationship between faith and science? Many people see that as sort of a conflict, that you can either have faith or you can have evolution. How do you see that relationship?
So I never saw it as a conflict. For me, science is actually something that brings you closer to God. Doing science and marveling at the deep relationships in the world is something that brings you closer to God. And I would argue this works in the following way, that if you think that science detracts from God, usually this comes together with a worldview where you say that the material world is everything there is, and everything that can be explained is actually a science. This is a worldview that one could call naturalism or materialism or atheism. And I would argue that the practicing science, that there's actually something wrong with this world. Because what the worldview overlooks really is something very important, and that is mathematics. Because if you think that science explains everything, the question is immediately not about mathematics. Science does not explain mathematics. So if mathematical theory has been proven, then the truth value has become known to us, and it's not necessary that a scientist now performs an experiment test whether there's something true about this theory. So mathematical truth is independent. Mathematics can be motivated by science. We ask certain questions that come up in the physical context in biology, but it does not need science in order to find truth. So then we can reverse the question, does science need mathematics in order to find truth? And the answer is yes, absolutely. Because the best possible science in physics and in biology or computer science is completely mathematical. So real scientific understanding is over the mathematical scientific. So now we have realized that science needs mathematics, and now we can ask, where does this mathematics even live? So where is mathematics? So mathematics is not in the material world. Mathematics is not in time, because mathematical truth is actually timeless. So science, which describes the material world, the unfolding of the material world in time, is actually dependent on something which is immaterial and outside of time. And for me, this is a step toward the divine. So for me, mathematics there's something divine about mathematics, and there's something divine about the way how mathematics interacts and guides the material. And therefore, I would say science itself brings you to mathematics, and therefore.
I think you said it really beautifully in your talk today. I might get this quote wrong, but I think it was something like, science is the study of the material world using the immaterial basis of mathematics.
Yes, I think that's absolutely right. And we have to ask, how does that work? Why is it that mathematical objects determine how this happening? And for me, this interaction that I consider very much divine. So for me, this is the creation.
Wonderful. And then you also have another new book which I just got. It's called Beyond. And tell us a little bit about this book. It's very different from the other. I mean, so you have, I didn't mention the other one, Evolution, Games, and God, which is, I mean, could you get a more interesting title for a book on it? But that's another one I have that was you and Sarah Coakley edited. But tell us about your new book, Beyond.
So for a very long time, I have been wanting to write a book that is about science and religion, that brings them together, and I have started to write this in the standard style of a non-fiction kind of trade book. But at some stage in the process, I realized that in order to be really true to the task, I also wanted in that style, and need a new style. And the style that I was looking for was that the topics are being discussed in the conversation between people. But in this conversation, there's also something recurring, which is a study, sort of an attraction of the beauty of the world, of the beauty of love and of God. And then this book developed into a Platonic dialogue, into a Socratic love story. And the idea of this book is really to make people aware of how beautiful the world is, how beautiful life is, and science and mathematics. And the hope is that some souls might be moved by this book to really fall in love with God, because I think this is the life.
Well, if the book doesn't do that job, then I think your witness will do the job. I think you're a wonderful witness as a great scientist, and also a very joyful Catholic as well. So thank you so much, Dr. Nowak.
Thank you.